Bismillahirrahmanirrahim. Hello everyone, I hope you are all doing well. I welcome you all in class of real analysis. In today's lecture, we will discuss an important and core topic of real analysis, that is inverse of a function or simply inverse function. I am using here Introduction to Real Analysis by Robert G. Bartle. So let us discuss. I have written if f is a function from a into b, then it is not generally true that its inverse is also a function. But if f from a to b is a bijection or a bijective function of a onto b, then its inverse is always a function. In this case, inverse of f is denoted by f inverse, also called inverse of f. What does mean by this paragraph? This paragraph simply says if your function f is a bijective function, then its inverse is always a function. But if your function is not a bijective, if it is either simply a surjective function or an injective function, then in that case, its inverse is not a function. It shows just an inverse relation. We will prove this claim by some examples algebraically, graphically, and from the set theory. But before going to discuss, these are some key facts. Remember that, as you know, A cross B always represents the Cartesian product of two sets A and B. That is actually the set of all order pairs A comma B, where the first element belongs to set A, that is the domain of F, and the second set B belong to the codomain. So, and every subset of A cross B is called binary relation. Every subset of A cross B is called binary relation, and f, the function f, is a one of the type of binary relation. So that's why I am writing here f is a subset of A cross B. If f is a subset of A cross B, then its inverse, f inverse, is always a subset of B cross A. That is just obtained by swapping the elements A and B like this, B comma A, where A is belong to the first set A and B belong to the second set B. The third point is domain of f is always equal to range of f inverse. Similarly, the range of f is always equal to domain of f inverse. And this is one of the most important point of today's lecture. If f is a bijective function from A onto B, then its inverse f inverse is also a bijective function. Consider a very simple example from set theory. In this example, I will show that if your function f is not a bijective function, then its inverse relation could be exist, but that not be a bijective, that not be a function. Take set A 1 comma 2 comma 3 and B is a set A comma B comma C. This is the A cross B, that is the Cartesian product of A cross B. Let F1, that is the subset of A cross B, consist on these three order pairs 1 comma A, 2 comma A, and 3 comma A. Clearly F1 is a function. From the set theory, you know, F1 is called function if it satisfies these two axioms. The domain of F1 should be equal to the first elements, first set, sorry. What is the domain? Domain is the set consists on the first elements of each order pair, which are 1, 2, 3. So the domain of F1 is equal to A. The second condition for function is that there should no repetition in the first element of every order pair. So you can see here there is no repetition in the first element of each order pair. This is a 1, this is 2, and this is 3. So there is no repetition in the first element in each order pair. So clearly f1 is a function, but f1 is not a f1 is not a bijective function because f1 is called bijective function if it is surjective as well as injective. First, f1 is not a surjective function. It is also not a injective function because for injectivity, for injection or injectivity, the set theoretic definition says that there should no repetition in the second element. As the second element repeat here, so f1 is just a function. This is not an injective function and hence it is not a bijective function. It is also not a surjective function. For surjectivity, range of f1 should be equal to b. If you find the range is only singleton set A, which is not equal to B here. So this shows that f1 is neither injective nor surjective, and hence it is not a bijective function. So we can see that the inverse of f1 is given by the inverse of f1 you can find by just swapping the elements a comma 1, a comma 2, a comma 3. Now this just represent the inverse relation, and further you can check that this inverse relation is not a function because it does not meet the first condition of the function. Its domain, if you find its domain is just a singleton set A, which is not equal to set A here, not equal to set A. This shows that the inverse of f1 is not a function. On the other hand, if you choose f2, a subset of A cross B, like this 1 comma A, 2 comma B, 3 comma C. Clearly this is a bijective function from A on to B. You can check this is a surjective function as well as injective, and its inverse relation given by inverse relation by just swapping the elements A comma 1, B comma 2 and C comma 3 is clearly a bijective function. Thus the inverse of a bijection is a bijection. This is our important point of today's lecture. Next I am going to share an algebraic example that clearly shows the inverse of a bijective function is always bijective, but if your function is not bijective, then its inverse relation is not a function. So consider the algebraic function from R to R such that f of x is equal to x square. Clearly f of x is not a bijective function from R to R. You can see here from its graph. In last lecture, I discussed the criteria to check from the graph whether the given function is a bijective function or not. This red graph represents the graph of y is equal to x squared, that is a parabola. This is not a bijective function because if you cut the graph by a horizontal line, you will see every horizontal line cut the graph at 2 points. We say that a graph, if every horizontal line cuts the graph exactly at a 1 point, then that graph represents the graph of a bijective function. It means this y is equal to x square does not represent a bijective function, and consequently its inverse relation is not a function. Finally, you can check here, this is my function y is equal to x square. I am interested to find its inverse relation. That is obtained just by interchanging x and y. So I have x is equal to y square. From here, y is equal to plus minus x. This shows that for a unique value of x, there are two values of y that represent why this relation is not a function. Algebraically, you say if for a unique value of x there is a unique value of y, then we say that y is equal to f of x, a function. But when you put here x is equal to suppose 4, you have y is equal to plus minus 2, and both values are eligible because my codomain is set of real number r and domain is also set of real number r. So I can say here the inverse, this is just an inverse relation. This is wrong. Here it should be y is equal to plus minus x. So I can say that when this your function y is equal to x square is not a bijective, then its inverse relation is not a function. And you can verify it from its graph. This is the upper branch of y is equal to square root of x, and this is the lower branch of y is equal to minus square root of x. You know the criteria, graphical criteria to check whether the given graph represent a function or not. If you cut this graph by a vertical line, this vertical line cut both branches at 2 points, here and here. This shows that y is equal to plus minus under root x is not a function. But on the other hand, if we take y is equal to x cube, this is a bijection from R to R. This is a bijection from R to R, and consequently its inverse relation y is equal to cube root of x. This is also a bijection from R to R. That can be verified also from the graph. This purple graph represent the graph of y is equal to x cube. You can check here, if you cut this graph by a horizontal line, every horizontal line cut the graph exactly at one point here. This shows that this graph of y is equal to x cube is a graph of bijective function. Now, this black graph represents the graph of its inverse, that is y is equal to cube root of x. This cube root of x is a bijective function. This is a function, also it is a bijective function. If you apply here a vertical line test, you will see here every horizontal line, every vertical line cuts the graph exactly at one point. Further, if you draw a horizontal line here, you will see every horizontal line cuts the black graph exactly at one point also. This shows that if the inverse of a f is a function, if f is itself a bijective function. Next, restriction of f. As we have seen above, if the given function is not bijective, then its inverse relation is not a bijective function. But if we can make the given function a bijection, but we can make the given function a bijection if we restrict the domain. In this case, the function is called a restricted function. Mathematically, if f is a function from a to b is a function and a1 is a proper subset of a, we can define a new function f of 1 from a1 to b, where f of 1, values of f of 1 x can be obtained from the value of f of x, where x belongs to now a1. This function f1 is called the restriction of f to a1. Sometimes it is denoted by f is equal to f1 at a. For example, I discussed above the squaring function, that is the parabola f of x is equal to x square already. If f is a function from R to R, this is a squaring function that I discussed above here. This function f is neither injective nor surjective over R. You can verify it from graph. You can verify also mathematical criteria. This function is not an injective function. For example, Suppose I find the value at x is equal to -1, your answer is 1. If you plug in x is equal to 1, your answer is again 1. So for the two different pre-images, the images are same. This shows that this function is not injective. Further, its range should be a non-negative real number. But here this is R. That is a codomain actually of this function f of x. So this function is neither injective nor surjective over R. And this implies this function is not a bijective function. So it cannot have an inverse function. However, if we restrict its domain to the set A1 is equal to set of all non-negative real number, then the restriction f1 at A is a bijective function of A1 onto A1. Therefore, this restriction has an inverse function which is the positive square root of the function. If we define a new function f of 1 from a non-negative real number to non-negative real number such that f of 1x is equal to x square. Now this is a bijective function and its inverse function exists, that is simply a positive square root. Similarly, in your earlier classes, you read about trigonometric functions sine x, cosine. These functions are also not a bijective function over their domain for R real number R. However, by making suitable restriction of these functions, we can obtain the inverse sine and inverse cosine functions. Next, in the last segment of our lecture, we are discussing problem 20b from exercise section 1.1. This is an interesting problem. We need to show that if f is a bijection of A onto B, my target is to show that f inverse is also a bijective function from B onto A. We can see here diagrammatically, this problem says, suppose this is my set A and this is my set B. There is a mapping f from A to B, that is a bijective mapping. I need to show that there exists an inverse mapping from B to A, and this inverse mapping is a bijective mapping also. So in simple words, this problem says that the inverse of a bijective mapping or bijection, inverse of a bijective mapping is bijective. This is the problem that we have to prove. Given that f is a bijection from A onto B, as f is a bijective function, so it is clear that its inverse function exists. To prove the bijection of f inverse, we proceed as, my target is to show f inverse is a bijective function. I am writing here the basic definition of surjectivity of f and injectivity of f just for our revision. What does mean by the surjectivity of f? We say that f is a surjective function when for all y belong to B, there exists x belong to A such that y is equal to f of x. What does mean by this statement? This statement means for every image, elements of B are called images, and elements of set A are called pre-images. So this line says that for every image there exists a pre-image x belong to A such that that image can be written as f of x, y is equal to f of x here. This is the definition of surjective function. This is definition surjective definition of surjective function says that if there is some element here x1, x2, x3, when we apply f at x1 we have an image f of x1. Similarly, when we apply f on x2 we have an image f of x2. F is called a surjective function. Suppose this is y1, this is y2. F is called surjective function if for all y belong to B. For all y belong to B mean for every image. For every image there exists x belong to A. X belong to A mean there exists a pre-image. Such that this y can be written as y is equal to f of x. Y is equal to f of x mean y is an output that can be obtained by applying f on this pre-image x. So this is the definition of a surjective function. What does mean by the injectivity? Injectivity says that suppose there are the two elements x1 and x2 in the domain. Suppose f of x1 is equal to f of x2. Suppose these two images or these two outputs are same, we need to show that x1 is equal to x2. So as f is a bijection, so these two definitions are given here. We show that f inverse is a bijection of B onto A. Firstly, we show f inverse is a surjective function. For this, what I have to show here? To show f inverse is a surjective function, I need to show the f inverse is a function from B to A. Now my target is to show f inverse is a surjective function from B to A. For this I need to show for all y belong to B, for all y for all x belong to A, there exists a y is equal to f of x belong to B such that when I apply f inverse on this y, I get answer x. Then I call f inverse a surjective function. As for all x belong to A, there exists a y is equal to f of x belong to B such that when I apply f inverse on y, as y is f of x, now f inverse and f both are the inverse function of each other. So from here I have f inverse, after cancellation f inverse and f give identity function ix, and identity function gives the same value as we give input here. So I of x is equal to simply x. So when f inverse and f both are the inverse function of each other, this will give x. This shows that f inverse is a surjective function or a surjection. To show injection of an f inverse, we show that we take two elements y1 and y2 from B. As f inverse start from B to A, so we will choose here both elements from the starting set B here. For all y1 and y2 belong to B, if f inverse y1 is equal to f inverse y2, we show that y1 is equal to y2 here. Suppose these two values are equal, and suppose their common value is x naught here. I am applying f on both sides here by applying f in first part and also here fx naught, and f and f inverse both are the inverse function of each other, so this gives us simply y1. From here I have y2, which is equal to fx naught. This shows that y1 and y2 both have the same common value f of x naught. This implies y1 is equal to y2, which is my required. This shows that as f inverse is both surjection and injection of B onto A, implies f inverse is a bijection of B onto A. So I hope today's lecture is helpful for you. If you have any query, any question, you can comments me. Inshallah, I will comment, I will reply. So if you find my lecture are helpful for you, kindly like and share. In the next lecture, we will discuss composition of function. So see you in the next lecture. Take care. Allah Hafiz.